I'm going to begin a new series called Modeling Distributions. Not surprisingly, the first question we should address is, what is a distribution model? When we look at a distribution of data for a variable, one characteristic of these data is that the distribution has a certain shape. That shape can sometimes be approximated by a mathematical formula. Here's an example. This histogram looks a bit like a rectangle. That's because along the entire score range, we have almost the same number of units in each score interval. This can be approximately pictured with a simple mathematical function that returns a constant, in this case 50, for every score that we put into the function. This results in a straight line along the top of the distribution. The mathematical formula is not a perfect description of the data. Mathematical formulas seldom match our data distributions exactly, but that's okay. It's not our purpose to represent the data exactly, but rather to provide a general impression of the distribution. If I obtain another set of data for the same variable, the peaks and valleys in the histogram will be a bit different than in the distribution we're looking at here. The mathematical model helps us picture the basic nature of these distributions and not the exact specifics, such as the small differences of frequencies that may occur across the range of scores. In other words, a distribution model provides a conceptual understanding of the distribution even without seeing a set of data. Here's another example. This is called an exponential distribution. An exponential distribution has a slope to it, like a hill. We would expect a distribution like this if we were studying the life of a machine or an appliance, such as a light bulb. In the early weeks and months of use, all the light bulbs in our data set would be working. If the score axis represents the amount of time that has gone by, we would expect some of the light bulbs to start burning out as we move along the horizontal axis. After much time, maybe only a few of the light bulbs will still be burning. There's a mathematical model for a slope like the one we see here, and this mathematical model can do a nice job of representing what happens to light bulbs over time. Even if we removed the histogram from this picture and just leave the mathematical model of the slope, we can understand something about the variable representing the number of burning light bulbs. Mathematical models provide conceptual understanding of a distribution. A mathematical model can be adapted to various contexts by changing parameters. We looked at one uniform distribution, but there are many uniform distributions, and each matches a different context. Mathematically, we say that we change the values of the function, which we call parameters, to create a new uniform distribution. Think about what we might be able to change in this picture and still have a rectangular box. We could change the height of the frequency and still have a uniform distribution. We could change the lower and upper bounds and still have a uniform distribution. The point is that there are many uniform distributions possible. Anytime we have data for which the frequency of observations is similar for every score interval along the range of scores, we would have a uniform distribution. These distributions differ from one data set to another depending on context, but they're all recognized as being uniform because they form a rectangle. Similarly, for exponential distributions, we could change the parameters to change the amount of slope. We can even change the slope so that it moves uphill from left to right instead of downhill. What kind of variable might yield this kind of exponential distribution? What if we were breeding fruit flies? We start out with 2 fruit flies, but as time goes by, we find more and more and more fruit flies in our breeding jar, so that the frequency of fruit flies over time will increase. The best mathematical model would be a sloping upwards hill. This is an exponential distribution, but one with different parameters in the mathematical function than if we were modeling the life of a light bulb. A distribution model helps us study distributional characteristics even with a limited number of observations. In fact, if we know that a variable follows a distribution model, we do not even need to have data to understand something about the variable. Here's a mathematical model which we call a normal distribution. You're going to be learning more about normal distributions because they are unquestionably the most important distributions in statistics. Some people refer to a normal distribution as a bell curve. In this model, most of the data is near the center or mean score of the variable, but as we get further and further away in each direction from the mean, the number of units with those scores decrease. Once we get out near the so-called tails of the distribution, there are very few observations with these scores. Many standardized tests are designed so that the scores follow a normal distribution. We can know a lot about the properties of a test by knowing that it is modeled by a normal distribution and by knowing the parameters of that normal distribution, even if we don't even look at data obtained from test takers. That's what I mean when I say that a distribution model allows for the study of distributional characteristics with limited observations. So to review, in a distribution model, the distributional form is approximated by a mathematical formula. This provides a conceptual understanding about the major features of the distribution. One model can be changed for different variables by changing the parameters. That is, there are many uniform distributions, many exponential distributions, and many normal distributions. And these are just 3 of the many mathematical models that are used in statistics. A distribution model allows for the study of distributional characteristics with a limited number of observations. As we move forward in our study, you will learn more about how understanding distribution models helps us understand the nature of the variables in our research studies.